Hi everyone, welcome to thechemistryuniverse.com. And in this particular video, we'll be continuing with our quantum mechanics lecture. In the last one, we talked about what is a wave equation. What is the meaning of a time-independent wave equation or the meaning of a time-dependent wave equation? And now we're going to go one step further. Now we're going to start developing the Schrodinger wave equation. Now, as I said, the Schrodinger wave equation is the equivalent of the Newtonian mechanics for classical physics. For quantum physics, it is the Schrodinger wave equation. And we're going to learn how to develop that, both the time independent and the time dependent. But before we do that, we need to understand certain things about partial derivatives. So let's get on with the video and start with partial differentiation. So first we'll see the partial differentiation of wave equation. And before we move on to quantum mechanical model of an atom, it is vital to understand the concept of partial differentiation. Now, if you remember, the time-dependent wave equation of a simple sinusoidal wave that we saw in the last video, and in case you haven't checked it up, please go and have a look at it, was y equal to a sine 2 pi x over lambda minus 2 pi t over t, where x is the horizontal displacement, small t is the time elapsed, lambda is the wavelength, and capital T is the time period of the wave. Now we are going to make an assertion here. This 2 pi x over lambda, here I'm going to call 2 pi by lambda as k. And it's not just, I'm just substituting this constant by another constant. It makes a sense because if you remember, 1 by lambda was called wave number. We saw that in Bohr's model. Now, what is the meaning of wave number? What wave number means is that if the wave travels lambda meters or lambda units, it means you have one wave in it. So, if you travel from any point up to a distance lambda, you will get one complete wave. But if you travel a distance 1 unit, or let's say 1 meter, if this is in meters, then if you travel lambda meters, you get one wave. If you travel 1 meter, the number of waves you will get is 1 over lambda. So that was wave number. Now I'm calling 2 pi by lambda as k. So what I mean by that is that when you travel lambda distance on a wave, the total angle traversed is 2 pi. So lambda meters you travel and the angle traversed is 2 pi. So if you travel 1 meter, the angle traversed will be 2 pi over lambda. So I'm calling this as k, and this has a significance that it is called angular wave number. So let us call 2 pi by lambda equal to k, and that k is actually called angular wave number. Now I'm also going to call 2 pi by t as omega, which is called angular velocity or angular frequency. Now what that means is that if you travel for t seconds, where t is the time period, then the angle traversed is 2 pi. And instead, you travel 1 second. In t seconds, the angle traversed by the wave is 2 pi. If it travels just 1 second, the angle traversed would be 2 pi by t. So this is called angular frequency or angular velocity. So 2 pi by t is omega, which represents angular velocity or angular frequency. So if I substitute both of that in this equation, I get y equals a sine kx minus omega t. Let's call this as equation 1. Now, what does partial derivative mean? Partial derivative means that you have y on one side. On the other side, you got two variables. And in this case, you have x and t. So if I differentiate y with respect to x, because you can't differentiate y with respect to two of the variables at the same time, you'll differentiate it with respect to one variable first. So when I do dy by dx, I'm going to assume t is constant. We'll follow the chain rule. So differentiate the value of y with respect to x, and then you can separately differentiate y with respect to t. When you differentiate with respect to x, you keep t as constant. When you differentiate with respect to t, you keep the x as constant. So that is the meaning of partial derivative. Okay, so partial derivative of a function with respect to a particular variable is the differential of that function with respect to that chosen variable, keeping all other variables constant. So let us take the partial derivative of function 1 with respect to x. This means we will assume small t is a constant. So if this is the equation, what will be dy by dx? Obviously, a will remain the same. Sine will become cosine. And inside, you will have kx minus omega t as it is. And then we'll multiply by the differential of the angle. Now, omega t being a constant, its derivative is 0. The differential of kx will be k. And therefore, the equation becomes dou y by dou x is a cos kx minus omega t into k. And this partial differentiation I'm calling as dou y by dou x. So in other words, dou y by dou x is ka cos kx minus omega t. Now let us do the same with respect to, now let's take the second differential of this equation with respect to x again. So this is equation 2. Let us now take the second partial derivative of the equation 1 or the partial derivative of equation 2 with respect to x. Either we take the second derivative of 1 or first derivative of 2. So that will become dou 2y by dou x2 equal to, now the cosine will become minus sine. So Ka remains as it is. It becomes minus sine kx minus omega t, and I have another k because I have to differentiate the angle. So got another k here. So this will become k square minus k square a sine kx minus omega t. Now let's do the same with respect to t. And I'm calling it as 3. So let's take it with respect to t. So let us take the partial derivative of function 1 with respect to t. This means we will assume x is a constant. So I get this. Because if you remember, the equation was y equal to a sine kx minus omega t. So when you differentiate this with respect to t, a will remain as it is. This will become cosine. Kx will remain the constant. And the differential of minus omega t will be minus omega. So that's why the minus omega is here. So rewriting this, we get this. Now let's take the second differential. Let us now take the second partial derivative of the equation 1 or the partial derivative of equation 4 with respect to t. Now dou 2y by dou t2 would be minus omega square. Now how do I get this? There's already a negative. Now the cosine differentiation will give me sine, negative sine, and negative will become positive. But again, I'll get a negative omega because I have to differentiate this. So I still have a residual negative here. And that omega and this omega will become omega square, a sine kx minus omega t. This is equation number 5. Now, if we multiply this equation 5 by k square omega square on both sides, so if we multiply equation 5 by k square upon omega square, we will get k square omega square dou 2y by dou t2 equal to negative omega square a sin kx minus omega t, k square upon omega square. Now, as you can see, the omega square will get cancelled and I'll be left with a negative k square. Now, if I just take you to the previous slide, you will notice something. Dou 2y by dou x2 was negative k square a sin kx minus omega t. So, that means what we have essentially got is that k square omega square dou 2y by dou t2 is actually dou 2y by dou x2. Therefore, k square upon omega square dou 2y by dou t2 is dou square y by dou x square. And here I would like to make sure that as you're watching this, please note down the derivation on your own, because we'll have to keep going back and forth. So rather than going through the previous slides, you should be able to go back to the equations that you've written on your notebook and check with what I'm saying. So that will help you understand this derivation better. Okay. So now we already know k is 2 pi by lambda and omega is 2 pi by t, which is 2 pi nu. So k square omega square would be, this k square omega square will be this square upon this square. And this, if you remember, 2 pi gets cancelled and this becomes 1 by lambda nu square. And lambda nu, if you know, is velocity. This is nu, this is v. So lambda nu is velocity. So 1 by lambda nu whole square is 1 by v square. So another way of writing this is 1 by v square dou 2y by dou t2 is dou 2y by dou x2, or in other words, dou 2y by dou t2 is v square into dou 2y by dou x2. Please make sure that you remember this equation because we are going to use it in the end. Now, this is where things get interesting. Now, what we're going to do is we are going to use a simple wave equation and use that wave equation to get a differential equation. Now, later on in one of the videos, I'll help you understand that differential equations have many solutions and some of them have infinite solutions. So almost any solution is possible. So therefore, rather than trying to get the wave equation, the Schrodinger wave equation, we'll get the Schrodinger differential wave equation, a second degree differential equation on the wave equation side. So we will use a simple wave equation to get the differential equation. Solving the differential equation would give us many solutions, one of which would be this particular simple equation. But when we want to get the Schrodinger wave equation, after solving that, we'll put a lot of conditions in it, which will help us get one clear equation from that. So that is the way we're going to solve the Schrodinger wave equation. And I'm not going to actually show you how we're going to solve it. We are only going to learn how to get the differential wave equation of the Schrodinger equation. And to get that, we'll use a simple equation. But that simple equation will not be the solution for this differential equation. It will be one of the solutions. But when we put all various constraints in it, and I'll tell you what is meant by boundary conditions, I'll talk about what is normalization of a wave function. When we do all of that, we'll get a unique equation that satisfies all conditions, which would be the solved Schrodinger wave equation. Okay, so now let's move on to Schrodinger wave equation, which is the time independent version. First of all, we'll see the time independent one. Now, the Schrodinger wave equation is based on the wave particle duality of an electron, which we already know. And this was developed by Erwin Schrodinger in 1926. And maybe in one of the other videos, I'll give you a brief history of how these things developed. Because the wave equation, one was being developed by Erwin Schrodinger using the wave equation, and the other was being done by Heisenberg and Max Born using matrices. And that was much more complicated than this. Eventually, they reached the same conclusion. So, this model describes electron as a 3D wave in an electric field of the nucleus. And as I mentioned earlier, just as Newton's laws are fundamental laws of classical mechanics, the Schrodinger wave equation is the fundamental law of quantum mechanics. And based on classical mechanics, a wave equation in the double differential form, which we just got, is expressed as dou 2y by dou t2 equal to v square into dou 2y by dou x2. Now, to convert this for quantum mechanics, Schrodinger first of all, and let's again call this, and let's call this as equation 1. To convert this for quantum mechanics, Schrodinger first replaced y with psi. Now, one may feel you're just replacing the symbol, so what difference is it going to make? Well, psi has much more greater significance in quantum mechanics than merely y. Y tells you the vertical displacement of the wave, that's all. Psi here is going to talk about a lot about the electron. It will describe the electron in all its glorious ways. So psi has more meaning in quantum mechanics than y has in classical mechanics. And here, it gives a complete description of the state of an electron, which uncertainty principle allows us to learn. So whatever uncertainty principle tells us that we can learn, we'll get it from this. In keeping with uncertainty principle, it gives us the probability of finding an electron in a given space rather than locating its exact position. So we're going to talk in terms of probability. Now, psi can be a function in the Cartesian coordinates x, y, z, or can be a function of x, y, z, and t. This leads us to both time-independent and time-dependent wave equations. Now, in a unidimensional system, if I were to just change this equation 1 from y to psi, it's going to be like this. In a unidimensional system, the equation can be written as dou 2 psi upon dou t2 is v square dou 2 psi upon dou x2. Whereas if I do the same thing in a three-dimensional system, this is equation 2, and if I write it in a three-dimensional system, the equation can be written as dou 2 psi upon dou t2 is v square dou 2 psi upon dou x2 plus dou 2 y upon dou y2 plus dou 2 psi by dou z2. And I can combine all these terms, dou 2 upon dou x2, dou 2 upon dou y2, dou 2 upon dou z2, because all of them are being performed on y, and this can be written as v square into dou 2 upon dou x2, dou 2 upon dou y2 plus dou 2 upon dou z2 on psi. Remember, they're not being multiplied. These are operations being performed on psi. So we can combine all the operations on one side, and therefore this is called an operator, and this is actually called the Laplacian operator, and it's called del. So eventually we get dou 2 psi by dou t2 is v square del psi. So this is v square, this is del psi. Remember, del psi is an operation being performed on psi and not multiplied, whereas v square is multiplied. Now, this is the equation of a wave moving in 3 dimensions. Now, equation 2 is a second order differential equation if the wave is moving in the x direction. Remember this one? This was equation 2. Now, the general solution for a time-independent wave equation, which we got from classical mechanics, was this. And where amplitude is replaced by psi naught, y is replaced by psi, and if you remember, in the time-independent one, we only got this. Now, I'm going to use this. I'm going to use this equation to get the differential form of Schrodinger time independent wave equation. And as I said, I'm using a simple equation to get that. On solving that, I'll get many solutions, one of which would be this itself. But when we put all the necessary conditions, which allows the electron to exist in an atom, then we'll get one unique solution, which is the Schrodinger wave equation time independent. So what is psi? It's a wave function. What is psi naught? It's the amplitude of the wave. Lambda is the wavelength of the wave. And x is the distance along the x direction. Now differentiating this equation with respect to x, we get dou psi upon dou x is psi naught cos 2 pi x into 2 pi by lambda. As you can see, the differential of sine is cos, then we do differentiate the angle. So dou 2 psi upon dou x2 is minus psi naught sine 2 pi by lambda x into 2 pi by lambda the whole square, because again we are differentiating. In the differentiation of cos will be negative sign. Again we differentiate the inside thing, it's become 2 pi by lambda, and both 2 pi by lambda become 2 pi by lambda square. So basically dou 2 psi upon dou x2 is negative psi 2 pi by lambda whole square, because this thing, if you remember, is psi. Let's call this equation 4. I've renumbered the equations. So I hope you are clear up to this point. Now, according to the de Broglie hypothesis, lambda is h by mv. Remember? So what is lambda square? It is h square upon m square v square. And that can be rewritten as 2m into half mv square. Now the half mv square becomes kinetic energy. And I'm calling now this one as 5. So what is the total energy? Total energy is the sum of kinetic plus potential. And total energy, let's say, is E, is PE plus KE. And what is KE? It is E minus PE. And I'm calling PE, the potential energy, as V. So if I substitute here KE, KE will become lambda square equals h square 2m E minus V. And now if I substitute lambda square in equation 4. Now you may wonder what is equation 4. I'll just show you. Substituting this value of lambda square in equation 4. Equation 4 with this one. Remember? If I substitute lambda square here, I get this. Dou 2 psi upon dou x2 is negative psi 4 pi square upon h square 2m E minus V. And if I simplify this, I get dou 2 psi upon dou x2 is negative 8 pi square m h square E minus V psi. And remember here it is E minus V into psi. So basically dou 2 psi upon dou x2 plus 8 pi square m upon h square E minus V psi equal to 0. Now remember, this is only in the x. If you look at 3D, this dou 2 psi by dou x2 will contain all other factors. Dou 2 psi by dou x2 plus dou 2 psi by dou y2 plus dou 2 psi by dou z2 plus 8 pi square m upon h square E minus V psi equal to 0. And remember, all these were operators. So I can take all the operators to one side and then operate it on psi. That will be del. So del psi plus 8 pi square m upon h square E minus V psi is equal to 0. This is the Schrodinger time independent wave equation. So now let's get the time dependent one. Now here again we start dou 2 psi upon dou t2 is v squared dou 2 psi by dou x2. This we had initially called as equation 2. And since psi depends on all the 4 variables, the general solution of this equation will vary. Moreover, the wave formed by an electron is a standing wave or a combination of two or more waves. Now you have to understand this. The electron in an orbit is considered as a standing wave. And standing wave is formed when a wave goes and reflects back and comes back, and there is a fixed length. And in this, you will find some places of constructive interference, some place of destructive interference, and you will find it's a standing wave. It will not radiate energy. It's contained within that particular section of the wave. So, this makes the general solution of the time-dependent wave equation turn out to be a complex number. So, the general solution for time-dependent wave equation is this. Remember, I'm saying it's a general solution. It's not the only solution. There are many solutions possible. And rather than telling you how I got this from the above equation, what you can do is, you can use your time and you can do dou psi by dou x, then dou 2 psi by dou x2. You can get dou 2 psi by dou t2, and you will be able to get the previous equation, equation number 2. So when you perform all the functions, you will be able to get this. So rather than proving that from this I got this, I'm going to show you this is a solution, and from this you can get this, which validates this as being one of the solutions. And again, as I said, it's a very simplistic solution. This is not the Schrodinger wave equation. This is not the solution to it. But I'm going to use this to get the double differential form. And that, when solved with all the conditions, you will be able to get the actual Schrodinger time-dependent wave equation. So getting the differential equation is the key. Now again, differentiating this is equation number 6. Now for those of you who don't know what I is, remember I is the imaginary number where I square is -1. So it's a complex equation. So differentiating this with respect to t, we get, remember, how do you differentiate this? Psi naught will remain, e to the power this will remain, then you differentiate the numerator. Since you're differentiating with respect to time, ikx will be not differentiated, it will be 0. I omega t will give you a factor of I omega. So, dou psi by dou t is psi naught e to the power I kx minus omega t minus I omega, which can be rewritten like that. And in short, this is psi. So I can write it like this. This is my new equation number 7. Now, we know that omega is 2 pi by t, which is 2 pi nu. And according to Planck's equation, E is h nu. And substituting nu, the nu from here is going to be E by h. So substitute that nu here. I get 2 pi E by h. And therefore omega can be written as E upon h by 2 pi, where h by 2 pi is always a constant that keeps coming up everywhere. So we call it h bar or h cross. So h bar is basically h by 2 pi. And then differentiate, you have dou psi by dou t, remember here? So here I substitute this value of omega. Dou psi by dou t is minus I E by h bar omega. How do I get this? Because I is as it is there, omega is E by h bar psi. Now, if you look at this, E psi, and I take h and I on this side, so E psi is negative h bar by I dou psi by dou t. Now remember, I square is -1. So here, instead of -1, I write I square. So I can write it as I square h bar, I square h bar by I dou psi by dou t, and I'll get one of the I cancelled here. So this becomes I h bar dou psi by dou t. Equation 8. According to the Schrodinger time independent wave equation, if you remember, we had this and there was no time factor here, and the 8 could be written as 4 into 2. I'm just trying to get the 2 pi square at the bottom, rather the 4 pi square at the bottom, so that I can get h bar square. So I get this. I think this is pretty simple. And E minus V psi is E psi minus V psi. And what is E psi from here? I h bar dou psi by dou t. So substituting the value of E psi from equation 8, I get this. Now you can pause it anytime you want in case you're getting overwhelmed by this. It will be overwhelming because there are so many equations there. But remember, it's a very simple derivation. There's not much to it. So del psi, and I'm taking everything else on the other side, del psi will be this. And I can bring the h squared 2m on the other side along with the minus sign. And I can rewrite, I can bring the V psi here. I think you can get the hang of this. We are just about to reach the end now. And now what I do in the next step, I'll just rewrite this so that you can understand where we are starting from. And then what I'm going to do is psi is common. So I'm going to take the psi outside. Remember again, psi is not getting multiplied by del. It is operated on del, whereas V is getting multiplied with psi. And this particular term is called the H, the Hamiltonian operator, denoted by capital H. And remember, we had already gotten this somewhere. Just look at the previous one. Can you see this? I h bar dou psi by dou t is E psi. And this is H, so I get H psi is equal to E psi. So E psi is already this. So H psi, this entire thing is H, remember. H psi is E psi. And that is the Schrodinger time-dependent wave equation. And that is the end of this video also. So yeah, it was a pretty long video and there was a lot of derivations. There were a lot of stuff we did, a lot of equation to write. And you can only get this, not by simply seeing it, you have to write it down on your own. And practice it as many times as you want. Now, generally, you are never asked the differential, the way we derive it. Nobody asks you the derivation. The purpose of doing that is, in most of the classes, in most of the schools and colleges, you're simply taught the final equation of Schrodinger wave equation. And most of us wonder, how did we get this? We got it from here. We took a simple wave equation and we differentiated that and we got the differential form. And then we say, okay, this differential form is the key, because solving this will give us the Schrodinger wave equation. But while solving it, we need to keep certain constraints in mind. When you put all those constraints, you'll get the eventual Schrodinger wave equation. So I hope you were able to understand everything that was taught in this video. See this video as many times as you want. And I hope you also enjoyed this video. And if you enjoy videos like this, keep looking at our channel, keep looking at this site, keep looking at our videos. We'll put more and more videos of this kind. And with that, this is Kalyan Kumar signing off. Have a wonderful day. Goodbye and thank you for watching this.